We gotta do a nice. We gotta do a nice pan.
Alright, today we're going to be doing 1978 Mechanics 2.
I'm expecting my old students to honor me and impress me with their fabulous knowledge from last year's edition. And I know for a fact that I gave them the basis of this particular problem.
Miss Todd did nothing.
True fact, true fact.
Alright, so this is a very interesting problem. We have, I'll do an example. I need a rod. Hold up. Okay. So we have a rod and we have a ball. We got the rod. We have a rod and we have a ball. And the rod is initially rotating with an angular speed omega on a horizontal frictionless table. So this is completely frictionless. And about a vertical axis fixed right here at point P. Just to, ready? Point P. And it's rotating fixed there. And it's going to come down, it's going to hit this ball. And then it's going to stop right when it hits it. And this ball is going to keep going. So it's a transfer of momentum to the ball. It's okay. We'll persevere.
She forgot me.
She's still here in spirit.
I can't believe she forgot me. This is not okay.
Alright, so we experienced some technical difficulties due to low memory before, so we'll go quickly. In this problem, we have this rod, this ball is at rest. This rod is on a frictionless table, moving with an angular velocity omega. It swings over and it attacks this ball, and it stops completely once it hits it, so then it's at rest after the collision, and this ball gets, from the force exerted by this rod, gets velocity in that way. So this is going to be a momentum problem. We're going to use, initially, we're going to use angular momentum. Hold on 1 second. I don't know why I used 1/2. Okay. So we're going to have the moment of inertia of the rod times the angular velocity of the rod is going to be, because angular momentum before, the initial angular momentum is going to be equal to the final angular momentum. Angular momentum is conserved because it's a question at the end, but there is no external torque on the system. So the angular momentum is going to be conserved, and we're going to have moment of inertia of the rod times the angular velocity of the rod. And then we can even though this ball here is moving translationally, right after the collision, we can say that it's moving rotationally, because it's immediately after the collision, its instantaneous velocity is going to be in the same direction regardless of whether it's moving linearly or rotationally. And so we're going to say the rotational velocity of this ball right after the collision is its velocity over the length of the rod. So then we can find the moment of inertia of the rod. It's given to us around its end is 1/3 m1 L squared, which is mass of the rod times the length. Then we have omega there, and then we can find the moment of inertia of this ball. It's a point mass, so it's just going to be the mass times the length squared. And so we can solve that using algebra. Get this velocity of the ball after the collision is going to be m1 L omega over 3 m2. Alright.
Okay, so part B was determine the linear momentum of the system just before the collision in terms of m1, L, and omega. So basically, before the collision, you had the ball and the rod, but since the ball is not moving, we just set that to 0. Then, so linear momentum is mv, and since this has a rotational movement, we can just use its angular velocity, which is omega, and then multiply by L to get the linear velocity. So then we get that the initial linear momentum is m1 omega L.
Okay, and then the next question asks, it says determine the linear momentum of the system just after the collision. So that's going to be right after it hits. And so then we're going to have velocity of the ball or the momentum of the ball, momentum of the rod. The rod is not moving, so that goes to 0 this time, and we just have mass of the ball times velocity of the ball. This velocity, we already have that over here, so we plug that in and solve that out algebraically. These M2s cancel out, so the mass of the ball actually has nothing to do with the linear momentum of the system, so it's going to be 1/3 M1 L omega.
Okay, now looking at part D, what is responsible for the change in the linear momentum of the system during the collision? Clearly from here to here there's a change in the linear momentum, and the reason for this is that we have an external force acting on the system, which is the force of the pivot on the rod. So since we have this external force, linear momentum is not conserved. But the reason that angular momentum is conserved is because we don't have a net torque. Because if you look at where the force of the pivot is acting, it's acting, and then we have the pivot in this, or sorry, we have the fulcrum in the same spot. So the distance from the fulcrum is 0. So there's no external torque acting on the system. So
And
that's why
that is 1978 M2.
Miss Cam didn't really help us.
She helped us in spirit, and she as she
spirit.
said, she gave us the basis for solving this problem.
All right, thanks, guys.
And Miss Todd's an amazing teacher. I was kidding.
beautiful
in the beginning of the
woman.
video.